In this video, I will be solving a simple linear program, a maximization problem. We have two variables, a and b, and we're maximizing 3a plus 4b. And we have one constraint that says a plus b is less than or equal to 10, b is less than or equal to 8, 4a plus b is less than or equal to 20. And then we have non-negativity constraints. A and b have to be greater than or equal to 0. I'll graph A on the horizontal axis, B on the vertical axis. Step number one is to find the endpoints of these lines so I can graph them on my graph here. So the process is really quite simple. Put in 0 for A and see what value B would have to make the constraint be an equality, and then do the same thing for putting in a 0 value for B. So I'm going to try to do a little color coding. We'll see how this works out. On the first constraint, if A is 0, then B has to be 10. So that'll be 0, 10. And then if B is 0, same thing, A is 10. So we'll have 0, 10, and 10, 0 on our first constraint. On our second constraint, no matter what, well, actually, let's try. No matter what, B is just always equal to 8. Always, always, always. And then on our third constraint, if we put in 0 for A, then we have B is equal to 20. So that would be 0 and 20. No, that got a little small, sorry. And then if we put in 0 for B, then we have 4A equals 20. So A equals 5. So that's 5, 0. All right, now I found all the endpoints, so I am ready to draw my picture, my lines. So on my y-axis, I have a value of 10, or b-axis, I have a value of 10 and a value of 8, and then a value of 20. So 20 is the biggest number I need to be able to draw here. So that's going to be 20 up there, and then that's 0 down there. And then on my horizontal axis, I've got a 0 and a 10 and a 5. So 10 is the biggest thing I need to draw there. So if that's 10, that'll be 5. If that's 20, that's 10. Okay, so my first constraint, the orange line, I'm at 0 and 10. So that will be one endpoint there. And then the other endpoint is at 10. So that'll be over here. And I will try to draw not very straight line. Boy, that's not very straight. I'll give myself one more shot. Oh, look at that big ugly mess. Maybe we'll edit that out in post-production. I'll have my editing crew get right on that. Oh wait, my editing crew is me. All right, that's a straighter line. So that's our first constraint. The second constraint, B is just always equal to 8. So if this was 10, then 5 would be around there, and 7.5 is around there, so 8 would be right around there. And this, no matter what A is, B is always equal to 8. So that will be a perfectly horizontal line, something like that. And then our last constraint, which is, I guess that's green, we have over 0 up 20, so that's up here, and then we're at 5, and that's down here. And now I will draw a straightish line. Okay, our feasible region, where is that? A cannot go negative. So the vertical axis here is a constraint because A can't go less than 0. Similarly, our horizontal axis is what shows the window B going negative. So we have to be above the horizontal axis or on it. We have to be on or greater than the vertical axis. We have to be below the blue, below the green, below the orange. And so that leaves us this funny little polygon here, kind of a chopped off triangle. And the optimal point has to be one of the corner points of our feasible region. So theoretically, it could be down here, it could be here, it could be here, or theoretically it could be there. Now, let me just say one word about these last 2 points. Because this line is perfectly horizontal, b is always equal to 8, what do I know about these 2 points? Well, I know here a is 0 and b is 8. And over here, a is bigger than 0 and b is the same. So this point has more a than this point, but they have the same amount of b. So there's just no way this point could be the answer, because this one has to be better than it. And I only know that because the line is perfectly horizontal. If it was tipped a little bit or tipped a little bit, then I can't say for sure. But if we have a perfectly horizontal line or perfectly vertical line, we can ignore the point there on the axis. So we have these 3 points, and one of them is going to be the optimal point. Now this point down here, I know it's on my green constraint, and that's where a is 5 and b is 0. So that is the point 5, 0. Let's go for the intersection of the orange and the blue. So the orange constraint says a plus b is equal to 10 when we are right on the constraint. And then the blue constraint says b is equal to 8. Obviously this is very easy to solve for because I already know one of the answers. B is equal to 8. So I'll take 8 and stick it into the other equation. So we have a plus 8 equals 10. And now if I think really hard, I wonder what it could be. Yes, obviously a must be equal to 2. So that point is 2, 8. So I guess I'm going to write the corner points in pink. So that's 2, 8. And the other point we need to solve for is where the orange and the green intersect. So the green again, let me just draw a little line here to separate those. We have a plus b equals 10. And then our other constraint is 4a plus b equals 20. Okay. Now what I need to do here is I need to multiply usually one of these equations by something, or maybe both of them by something, so that they have the coefficient is the same. They have the same number as a coefficient, but I got lucky on this one because we have a b times 1 and a b times 1, so I don't need to do any multiplication. So I'm going to take the bottom one and subtract the top one off of it. So we have 4a minus a gets me 3a, b minus b, that's just 0b, so it just goes away. And then we have 20 minus 10 gives us 10, so a is 3.33, and so I know the value of a, and I could stick it into any one of these equations that I want. Obviously I'm going to choose the one that's easiest, so I'm going to choose the top one because I don't have to do any multiplication. So I have 3.33 plus b equals 10, so obviously b equals 6.67. And this point is 3.33 comma 6.67. So that goes right there. And so this was 3.33, 6.67. Okay, so I have found the corner points, and now I need to know which one is going to make us the most money. So I'm going to plug 2, 8, 3.3, 6.7, and 5, 0 into our objective function 3a plus 4b, and whichever one makes us the most money is the winner. Okay, so I don't know, go back to yellow, I guess. So I'm just going to make a little list of the points that we are looking at here, and the profits we get from each one. So we're going to have 2, 8, and we're going to have 3.33, 6.67, and then we're going to have 50. So the profits for the first one, that will be 3 times 2 plus 4 times 8. So 4 times 8 is 32 plus 6 is 38. And I don't have a live studio audience. I know, this is a big budget production. You assume I've got a whole studio audience here, but sadly I do not. Yes, so check my answers and make sure I don't do the math wrong. So yes, that was 38. Then for the next one, we have 3.33 and 6.67, so I'm putting that in for A and B again. So we have 3 times 3.33 plus 4 times 6.67, and that works out to 36.68. And then lastly, we have 3 times 5 plus 4 times 0, which is obviously 15. So of these 3 points, we could get $38 or $36.68, or we could get $15. Obviously, the winner here is $38, where the point is A is 2, B is 8. So this point right here is our optimal point to choose. And so we could say the answer is A equals 2, B equals 8, and the profits are $38. So just to recap, we had the linear program, we found the endpoints for each of the constraints, 0, 10, 10, 0, B is 8, 5, 0, and 0, 20. We drew those on our graph, and then we found the feasible region, and then we identified the corner points of the feasible region, and we're able to eliminate one because it's dominated, the mathematicians would say, by this other point. And then we needed to just solve for those corner points using just a little tiny bit of algebra. And then once we had those corner points, we had to find out how much profit we would get from each one, and then we chose the one that gave us the most profit because we are maximizing. I hope this has been helpful.